All right, this is my exam submission for exam number 2 for EGR 480. So after we import our ports, which is just as easy as the clock, the switch and LED arrays, and then these 7-segment display components, we can begin to set up our behaviors. So we have types here. These are enums, really easy to work with to define state. We have freeze, unlock, and lock for our main states. For our modes, we have set and verify. And then we have flags, correct, wrong, and idle that we use to determine the pulse rate of the LED. Then we actually assign these to signals and set their default state. Next, we have all the rest of our signals that we declare. We have our temporary number, so this actually holds whatever the current input of the switches is stored in here. We have our check set and mode pins. Check set will check the current value and compare it to the code when we're in verify mode, and it'll set it when we are in set mode. The mode pin determines what mode we're in, and then the reset pin sets everything back to its default values. We have the code itself. We have our count, which determines how many times we've gotten it wrong. We have our refresh. This is another counter that will determine how fast the anodes will refresh. We have our edge signal, which acts as a latch so that when the check switch is flipped up, it doesn't check multiple times per clock cycle, or it doesn't check over and over. And then we have our blink timer, which is another counter, just like refresh, but that determines the LED blinking. We have our constants to control these blinkings. So we have 1,000 hertz for the refresh rate of the anodes, 10 and 2 hertz respectively for the refresh rate of the LEDs. And then we have a character array to store the various characters that we're going to need to display once it's whenever it changes modes, and an index to cycle through for the anodes. So we can get into the actual logic here. This is our LED blinker. So if it's set to correct, then it increments the timer by 1. And if it's less than the 1 hertz, then if it's greater than the 1 hertz, it goes back down to 0, and then it either turns on or off, depending on what it was last. Same thing happens here when it's wrong, just at a 5 hertz instead of 1 hertz. And then if not, nothing blinks. Pretty simple. Next, we have our process that actually controls, this is the entire state machine, actually. So reset just resets all the various states, lock, set, and idle, and then our count and edge both go to 0. This is actually all the state that we need to save in order to return to the default position. Next, we have on rising edge. So if our mode pin is equal to 1, which means that we are in set mode, then it just goes to set mode, and all of the logic is basically encoded already. And then if not, we're in verified mode. So if it's in set mode, it's really easy. Nothing happens if check set is equal to 0, but if check set is equal to 1, then we move whatever the value is in temp into the code. And then if check set is equal to 1 and the edge is 0, and also implicitly because it's the else statement, we're in verify mode, then we use we keep track of the count here, use a case statement to match the count, and for our first 3 attempts, it just blinks that we're wrong by sending the wrong signal or correct signal, and then it either switches our state to ulock or it just counts up. And then once we've passed our threshold, then if it's wrong, it sends to freeze. And then lastly, the edge is equal to check set. That just is so that we can, again, up here, match against check set to make sure that we don't flip too many times with one flip of the switch, essentially because of the clock rate. So finally, we have our actual muxer and display matching here. So we cycle through the indexing by mod 4, since we only have 4 slot positions. And we turn on the various anodes as is required in time with the refresh rate. And then we can use our states again to determine what we actually send. So we just match against our state and then push into the character array these various characters, and then they are a separate process that's running in parallel actually checks those characters and turns on the 7-segment displays. So the 7-segment displays aren't actually on any sort of refresh rate, just the clock cycle itself. The only other thing there is our actual test bench code, which is pretty simple. After setting everything up, it just runs it through a few tests to make sure that everything's going correctly. So we have our reset pin, we have a code write, and then a verify, and then we have a couple wrong ones. So we can see it happening here on the actual simulated waveform graph. That this is the reset pin going high here. Oopsies. That's the reset pin going high there, and nothing changes after that because it was already in its default position. And then here we have our set mode and check set pin, and then we have our encoded value. And then if we go farther along, you can see it checks, and there is actually the blinking of the LED in 12 if we had let it go on longer, but it actually ends too quickly, unfortunately. Alrighty, so now we can go on to actually showcasing this thing. So by default, it's in the lock position. If we turn it to the set mode, that LED indicates it's in set mode, and then we can encode whatever value we want. We're going to go 1, 3, and 4, and then we're going to flip this up to encode it. All right, now it's encoded. So if we enter something wrong, like 2, and then we check it, as you can see, we're getting a wrong, incorrect fast blinking LED. Now we can do it again, still wrong, and again, still wrong, and we're frozen. So now what? Now we have to hit the reset pin. Sets it back. Everything is reset to its default position, so we can run through the same test again. So let's encode 1, 3, and 4 again, like we did the first time. Except this time, we are going to unlock it right away. And now it's blinking. And we can reset it again. So it is predictably working as a combination lock.